All right, show of hands. Who here likes greenfield projects? Too bad, this is the real world. My name's Ben Cates. I'm the lead web developer at System 76, and I'm here to talk to you about building on top of a legacy database. If you don't know who we are by this point, I really don't know what Shree's been doing. We've been in business for about 12 years now, and we started our startup phase the same way everyone else does: move fast, break things, just try and get features out the door as fast as we can. And so we have about a decade's worth of user data in an existing database. I don't know if anyone's seen the movie War Games, but our legacy system is a giant PHP monolith named Joshua. Joshua is Joshua's it's a giant PHP database. It was thrown together. Its features were just kind of shoved in wherever they fit. Worried about getting the features out the door and growing as fast as we could, and we'd deal with the technical debt when the bill came due. Well, about 2 years ago, the bill came due. Our CEO asked me to implement a feature, and I had to tell him no. We had a long meeting about what to do, and decided to bite the bullet and do a giant rewrite. And he asked me what I wanted to do it in, and I told him, well, there's this cool language called Elixir that hit 1.0 last week, and so we sat down and we decided to replace Joshua with a much cleaner, much friendlier, much more user-friendly program. Meet Hal. Hal is a pretty standard Phoenix application, but it is built. But we're a small team, and we didn't have time to go offline and do a giant rewrite. So we're having to replace in place. Joshua is still online. Hal and Joshua are sharing a database, and so we have to treat the schema as read-only. We have this giant database as is, and we have to kind of build on top of it, and we don't really get to do much with it. So we've kind of run into a number of we've kind of developed a number of techniques to deal with some of the pain points of building on a legacy database, and I'm going to tell a few war stories and kind of walk you through some of what we figured out, and hopefully it'll be helpful. Kind of broken this into 3 big sections: bad names, bad types, and bad structure. Bad names. First things first, and this is really simple, but this was one of those things that was so stupid it was difficult for me. Your schema names don't actually have to match your table names. My instinct when I was making schemas out of existing tables was to just name the schema whatever, or name the module and name the schema whatever the table was. You don't need to do that. The names don't have to line up. You can name them whatever you want. As a matter of fact, you probably should. With context in Phoenix, there's a difference there's an impedance mismatch in the naming scheme. You want you have the context and then the schema in the context in your code, but you probably want a simple descriptive name in your database. So feel free to just name the schema whatever, and it doesn't have to match the table. Second, field names don't have to match column names. So does anybody have any idea what these do? Yeah, me neither. How about now? The source attribute was introduced in Ecto 2.2, which came out August of last year. It allows you to give your fields an arbitrary name and map them to an arbitrary database column. If you're working with an existing table, don't feel trapped by the names. You are free to go in and name your fields whatever you want. Pick nice, good descriptive names, and then just map them to whatever. That concludes the easy part of this. Bad types. We have a lot of data in it that's stringly typed. We have a lot of data that's in unfortunate types that if I had the chance to go back in time and do differently, I would. Luckily, Ecto gives you a wonderful, wonderful tool to deal with this called Ecto Custom Types. You can define it. You can define a module that implements these 4 methods: type, cast, load, and dump. All of which are very, very simple. Type is the actual type of the database. Cast is what Ecto change sets actually use under the hood to cast user input into your struct, and load and dump write to and read from the database respectively. So we've used this to kind of retype a lot of our columns and to clean up a lot of our data types without actually having to touch the underlying schema. So I'll walk you through a couple of examples of this. We store a lot of money as float columns, which is unfortunate, like really unfortunate. Yeah, floats, because they have to hold the entire number line, because they map an infinite set to only 64 bytes of actual integer. They're approximations. They don't do it. They don't hold all legal values, and they don't always give exact values in arithmetic. Most of the time, that's not a problem. But if you're doing lots of arithmetic, if you're doing lots of complicated pricing calculations, if you're working with very large or very small numbers, you can be off by a couple of units at your smaller significant digits. And if you're charging people money, that's illegal. So what we should be doing is using the decimal library. This is a dependency of Ecto. It's in your projects, whether you wanted it to be or not. And the syntax is it's not the best thing in the world, but it does do actual arbitrary decimal math, and it and allows you to do arithmetic safely, allows you to do any money calculation safely, allows you to actually have cents and save you the trouble of converting from dollars to integer cents and back. So in our project, we actually want to use decimals for everything. We want to use the decimal library throughout, and so we on read and on write immediately convert our floats into decimals and use decimals throughout, and only convert back to floats immediately before writing to the database. And we've done that via creating a custom type called fake decimal. It's a very simple class. It's a very simple module. It just implements the Ecto type behavior. The type is float because that's the underlying database type. Dump and load are actually pretty trivial. We have to special case nil because nil's not a number, but it is a database value because databases are terrible. Other than that, we basically just lean on the decimal library's built-in conversion functions. Cast is a little bit more interesting. Cast is usually the only interesting method in these. Cast has to take user input, so you want it to take a wide variety of types. In our case, we're lucky because decimal new already takes a variety of types. It takes strings and integers and floats and a weird tuple syntax, and basically anything a user could pass in through a JSON API anyway. So we don't actually have to do much work here. All we have to do is catch the error and massage the output a little bit to give it the tuple it wants. And in our actual schemas, instead of giving it the decimal atom or the float atom, we can just give it the fake decimal module, and it all just works. In the rest of our code, we can treat price as though it were stored as a native decimal. We never have to we never have to do any explicit conversions. We never have to think about it again. Another quick example. Who likes these? Yeah, these are a pain to work with. I'd much rather be working with something that looks a lot more like this. But all of our timestamps in our database are UNIX timestamps. They're integer columns. They're integer and Joshua, the old code base, just does just does a whole lot of integer math and a whole lot of explicit conversions, and it's a mess. And I'm kind of amazed it's not buggier than it is. And we didn't want to do that in our new code base, so we introduced a custom type for Unix timestamps. Again, implements the ectotype behavior. The underlying type is an integer. Dump and load are just date time to and from Unix. And again, the only interesting part here is the cast method. Cast method takes a date. First clause takes a string, assumes it's an ISO 8601 string, a standard timestamp, and converts it to a date time. It accepts an incoming date time and passes it through unaltered, and otherwise it errors. Conspicuously absent from this are integers. You don't actually, even though the underlying data type is an integer, our API does not accept integers. We cannot work with them. Your ectotypes don't actually have to have any relation to the underlying type. Anything that you can do a two-way mapping on, you can use in your code base, and this will handle all of that for you. And we never see a bare integer in our code base. We use this to solve a bunch of different problems. We have comma-separated lists stored as strings. Note the leading and trailing commas. That's so you can do where like comma string comma. It's in our code there are lists of integers. We have an account type, which is a MySQL enum that's either business or individual. In our code base, those are atoms, and if you try and write another column into that, it's a change set. The change set throws a validation error. We have JSON stored as strings that we work with as objects. We have things that are encrypted at rest in the database that we see as bare strings, and we never have to think about the encryption. Honestly, this takes a whole lot of the pain out of our typing. It gives us the freedom to kind of have the types we wish we had without actually having to change the underlying schema. Third, bad structure, where the tables are just wrong, where the tables are, where it's something where it's extra columns or not enough columns, or something that should have been a table isn't, or something that should have been something that should have been a table isn't, or something that shouldn't have been a table is. And we've come up with a few techniques for dealing with these as well. First, this is our users table, or at least as much of it as I could fit on a slide. It's a lot, and there's a lot in here that's really pretty useless. Like this is a foreign key to a payment processor that went out of business like 4 years ago. This is an avatar that we haven't used in the site in half a decade. This is an IP address log for a fraud prevention program that isn't in production anymore. Like, most of this is actually just legacy stuff that we really don't need or want anymore. So this is the actual schema. We've only imported the fields we need. Everything else we just ignore. There is a caveat with this that doing inserts is a little tricky here. If you don't import the field, it needs to have a reasonable default, or it needs to be okay being null. But we're actually not creating any users through HAL yet. All of our user creation is through Joshua. We just do user updates and maintenance through HAL. So that hasn't bit us yet. So we're only importing the fields that we need. We keep a nice small schema. We keep a nice manageable object in our memory space, and we don't actually have to change the underlying table. Unnecessary tables. We have a couple of tables that shouldn't be tables. Things like order status. Like all of our orders have a status that's one of half a dozen things, in progress, awaiting payment, shipping, so on and so forth. And those are hard-coded everywhere in Joshua. They're hard-coded everywhere in HAL. Those cannot change. If we add or remove a row from that table, it will break. I don't even want to think about how much. So it's not really data. It's code. It shouldn't be in a database in the first place. But we've already got this table. We've already got our orders that have a foreign key to it. We've already got we've already got this association in this table that we don't want, and we can't drop it because that would break Joshua. So we've worked around this by just not creating a schema for the table. We've created a custom type instead. The type is integer because that's what our IDs are. We just hard code all of the legal values into a statuses object. We do a few mappings of that at compile time to get so that we can do really easy mappings into this. And we accept atoms or integers or binary versions of all of these and map to whatever the relevant integer is, and then we dump and load from atoms in user space to IDs on the database and back up. And then we added an extra function called name that takes the atom and gives you back a human readable name, which gives us the one other column on the database on the table that we actually care about. And we just don't import, and we just don't create a schema for it. Our orders table looks like this. It has a field named status with a type of order status that the source happens to be an order status ID. And as far as our code is concerned, this is just an enum. And because the values happen to match to legal values in the database, we can write to it, and it satisfies the foreign key constraints, and Joshua can pick it up and still follow the associations and find the record in the original table, and it all just works. We never have to think about it again. And finally, we have our hardest problem is structural duplication. This is what our order item looks like. It's got some shipping data on it that handles stuff we have to hand to UPS for them to actually build a package out of it. This is all pretty straightforward and self-explanatory. Unfortunately, this is also pretty straightforward and self-explanatory. Joshua just has about 1,000 lines of code copy-pasted. Yeah, I didn't want to do that. So we have something that should have been a join table but isn't. It should have never gotten duplicated in the first place, but now we're stuck with it. There's years of legacy data in it, and we can't really pull an object out of it, except that we can. We can pull a struct out of it. So we can just make a struct that is the schema that we wish we had had. Note the under original column in there. That's that's important. In our orders module, we can just have a to parcel that takes an order item and builds a parcel out of it. It's just a really simple mapping. Puts the original item in the original there. We have a from parcel that pulls the original out of the object and builds a change set out of it. And then when we want a parcel, we have the one call of to parcel and from there we get to basically pretend that it's a schema. It works exactly the same. There's no distinguishing in our code base, and we've completely papered over the problem, and we have a table that doesn't exist. And yeah, so bad names, Ecto gives us tools to work around. We can pick the names we want and trivially map to whatever we want. Bad types, we can use Ecto type to create the types we had originally wanted. And bad structure, we can with a little creativity we can create or remove tables without having to touch the underlying schema. The database is still a mess, but we in our user space get to pretend that it isn't. So, yeah, questions?
First off, before we get to questions, is that the last part? Go ahead and give him a round of applause. You ended your talk so casually. I was like, oh, wow. All right.
Yeah. Hey, thanks. That was a great talk and very familiar to me. So I was wondering if you guys had developed a good strategy for, I guess, resolving the differences between the two systems in terms of, you have the new schema that you want and how do you go about deprecating the old version, actually removing the values from the database or whatever changes you want to make?
Well, for now, we haven't, actually. We're doing it as a gradual rewrite, so Joshua is still in production. Most of it's still reading and writing from the database. As we add features and modify features, we're porting them over to HAL on an ad hoc basis. And as modules go away, honestly, most of my schemas just have a to-do under it that's the migration that I wish I could run. And as sections get written out of Joshua entirely, then we go through, we add migrations, we change the columns to whatever we wish they were, and we eliminate it. But honestly, it hasn't actually been that big of a problem for us.
Any more questions? Be sure to raise your hands high so I can see you. It's a lot of people.
Thanks. One of the legacy features that I used to like to build into databases was single table inheritance. Mm-hmm. And so now I have some projects where I'm porting an old Rails app to Elixir, and I was wondering if you had any ideas about working with databases that are structured that way, where I've got a bunch of different schema objects which are similar but not quite the same, and use the same underlying table.
Well, there's if you know what the type is, then you can actually build more than one schema out of the same table if you want to. We store our customers and our staff in the same accounts table, unfortunately. So we actually have two schemas developed out of that. You have to do a little bit of plumbing to make sure in your context when you're fetching that you filter by the relevant type column. But once you've done that, you can just read into two different schemas and have two different types, and just define two schemas that map to the same table, and the only place you have to deal with it is in your context. Oh, and add a field for type with a default value, or I would add a field for under type that mapped to the type column and had a default value set either in the schema or in my change set, so that when I created a new one through the right schema, it created the right type column, and again, never have to think about it.
So I'm wondering, how are you documenting your process of changing from a legacy app that's being taken over by another? And I'm asking for purely selfish reasons.
We're kind of doing it one module at a time. We're pulling a context out as we have a context that we wish was already in HAL. So we'll have a feature that we want, and we'll go ahead and port the entire context in, or at least most of the context in. We make extensive use of comments on in our schemas showing what they map to and where they come from. We have actually large blocks of PHP in comments in the middle of our modules, showing what the original code was and what we're porting from. We have a lot of to-dos that are this. I know this is stupid, but it has to be, basically, and that explains why. And we actually are. This was kind of a little outside the scope of the talk, but we make extensive use of type specs. We document our types pretty carefully. All of our schemas have, in addition to the schema definition, they have a type T that has all of that have all of them, and a type doc that documents what each column does, and with any gotchas around that particular data in that type doc comment. So that's kind of our go-to for impedance mismatches. That's kind of the one place we collect those in.
Let's give him another round of applause.